In analysing the Königsberg bridge crossing scenario, first and foremostly, it is clear that with the placement of bridge number 3, it is impossible to simply walk back and forth from island to island in a simple pattern. For instance, from bridge 1 to 5, 6 to 2, and 4 to 7. Likewise, after multiple attempts at various locations, including bridge number 3, it is evident that no matter what island or bridge the traveller begins at, there will always be one bridge left over, thus one bridge that they are required to walk over twice in order for all to be crossed. It can also be identified that there are an uneven number of bridges. Is the consequence of this the reason all bridges cannot be crossed only once? Can it be assumed that this odd number of bridges is the reason underlying the Königsberg Bridge situation? From research into this dilemma, a solution has been identified. In 1735, this question is answered by mathematician Leonhard Euler in his own investigation into the Königsberg bridges. Leonhard believed this issue could be referred to the topic of geometria situs, or geometry of position. Euler decided that instead of using numbers to represent the crossing of a bridge, he would write the capital letters representing the land masses. For instance, referencing figure 1, bridge AB would signify a journey that started in landmass A and ended in B. Likewise, if after travelling from landmass A to B, the traveller decides to move to landmass C, this would be simply denoted ABC. Euler continues his discussion on this process, explaining that in ABC, although there are 3 capital letters, only 2 bridges are crossed. He explains that no matter how many bridges there will always be one more letter to represent the necessary crossing. Because of this, the whole of the Königsberg Bridge problem required 7 bridges to be crossed, and therefore 8 capital letters. Subsequently, Euler claims that if the situation involves all land masses with an odd number of bridges, it is possible to tell whether a journey can be made using each bridge only once. His theory states that if the sum of the number of times each letter must appear is 1 more than the total number of bridges, a journey can be made. However, if this number of occurrences is greater than 1 more of the number of bridges, a journey cannot be made. So in reference to the Königsberg scenario, Euler claims that region A must appear 2 times, B 3 times, C 2 times, and D 2 times. But how did Euler reach that conclusion? This conclusion can be represented using a simple diagram of vertices, both adjacent and connected, and edges. 2 vertices are called adjacent if they are attached directly by one edge, while 2 vertices are called connected if they are connected by a sequence of edges. If a vertex is adjacent, then the letter representing that vertex must appear for every adjacent edge connected to it. However, if a vertex is connected, the letter only needs to appear once for each connection it is a part of. Referring to figure 2, each edge represents a bridge, while the vertices indicate the land masses. According to Euler, the sum of the number of times each letter must appear must equal to 8 for it to be possible to cross each bridge only once. Consequently, it can be identified that point A has 1 connected and 1 adjacent vertex, therefore must appear twice. However, B has 2 connected and 1 adjacent vertex, therefore must appear 3 times. Similar to A, C has 1 connected and 1 adjacent vertex, therefore must appear twice. And finally, D has 1 connected and 1 adjacent vertex, therefore must appear twice too. 2 plus 3 plus 2 plus 2 is 9, which is more than 8. Therefore the journey is possible. As stated previously, this is because Euler stated that if the number of occurrences is greater than 1 more than the number of bridges, a journey cannot be made. Therefore, from the results and observations of this theory, it can be deemed that the solution for this issue would be to simply add another bridge anywhere within the Königsberg area. This is because the location of the 8th bridge is irrelevant. The vital factor is that the sum of the number of times each letter must appear is one more than the total number of bridges. In reference to Figure 3, a new bridge has been added between Island B and D. So there are now 8 bridges. According to Euler, the sum of the number of times each letter must appear must now equal to 9 for it to be possible to cross each bridge only once. In analysing this new design in the form of vertices and edges, it can be identified that A has one connected and one adjacent vertex, therefore must appear twice. B now has 3 connected vertices, therefore must appear 3 times. C has one connected and one adjacent vertex, therefore must appear twice. And D now has 2 connected vertices, therefore must appear twice. 2 plus 3 plus 2 plus 2 is 9, which is 1 more than 8. Therefore, this journey is possible. Therefore, a new potential route for this model follows the path of bridge 1, 5, 6, 2, 4, 3, 8, then 7.